For many centuries, humans thought of the universe as a straightforward place. We assumed that our planet, Earth, was the center of all existence. The sun, stars, and other celestial bodies were thought to circle around our home in perfect harmony. This perception of the cosmos was largely a result of our natural tendency to place ourselves at the center of everything. However, as the human understanding of the universe evolved, we embarked on a journey that would eventually lead us to discover our true place in a sprawling galaxy known as the Milky Way. This journey of cosmic discovery is a fascinating tale of determination, innovative thinking, and scientific breakthroughs. To accurately identify our location within the Milky Way, it's imperative that we first understand the true structure of our galaxy. The night sky offers the first set of indicators, presenting us with a faint, luminescent band of stars, a celestial ribbon that we recognize as our galaxy. The band-like formation suggests that we inhabit a flattened disk rather than a spherical structure. Should our galaxy be spherical, we would witness a significantly higher distribution of stars, scattered evenly across the entire sky. Moreover, the band appears to bisect the night sky, implying that we exist within its plane, neither situated above nor beneath it. It remains impractical for us to vacate this plane to gain a full perspective of the Milky Way shape. Such a journey would require traversing hundreds or possibly thousands of light-years perpendicular to this plane. For context, consider Voyager 1, the most distant human-made object. Despite its near half-century of space travel, it has only covered a distance equivalent to 0.02 light-years. This underlines the magnitude of the distance that we would need to travel to fully observe the structure of the Milky Way. However, the lack of technology of direct observations did not dissuade us from determining the shape of our galaxy and our place in it. The first notable stride in this journey was taken in the 18th century by William Herschel, who is best known for his discovery of the planet Uranus in 1781. Herschel was not just an astronomer, he was a mapmaker of the cosmos. Herschel's primary tool in his investigations was his handmade telescope, a device that allowed him to peer deeper into the cosmos than anyone before him. He was a bold thinker and dared to take on a task that no one had ever attempted: to map the stars of the Milky Way. In the late 1700s, with the help of his sister Caroline, he embarked on a grand project. He divided the night sky into approximately 600 zones, and with relentless patience and precision, cataloged the position and brightness of each observable star within these areas. His process involved viewing the night sky through his telescope and marking the relative positions of the stars on a grid. His meticulous star count led him to propose that our galaxy was a disc-shaped structure. His observations also suggested that our solar system was close to the center of this structure. However, Herschel's map was not entirely accurate. He was unaware of the existence of interstellar dust, which blocks our view of stars in the Milky Way's central region. As a result, Herschel's map showed the central region of the Milky Way to be much less dense than it actually is. Despite its inaccuracies, his map was a major breakthrough in our understanding of the Milky Way. It was the first map to show the Milky Way as a disk, and it provided important clues about the structure of our galaxy. To introduce the next important character in our story, we jump ahead from the 18th century to the 20th century. Our destination is the Harvard College Observatory, where a curious astronomer with a deep fascination for the universe is observing something extraordinary. Her discovery is going to revolutionize the field of astronomy and change its course forever. It's often said that in the theater of cosmic discovery, every star plays a part. This holds true not only for celestial bodies, but also for the pioneering minds who've worked tirelessly to uncover the mysteries of the universe. Henrietta Swan Leavitt, an American astronomer, is one of these luminaries who made significant contributions to our understanding of the cosmos, thereby informing our knowledge of our place within the Milky Way. Leavitt's work focused on a unique type of star known as Cepheid variables. These stars have a peculiar property. They pulsate, growing brighter and dimmer over regular periods. Leavitt's job at the Harvard College Observatory involved cataloging these stars, a role that led her to a groundbreaking discovery. She cataloged 1,777 variable stars. In 1908, she observed that there was a direct relationship between the luminosity of these stars and their pulsation periods. Brighter Cepheids pulsed more slowly than their fainter counterparts. This simple yet profound relationship, now known as Leavitt's law, allowed astronomers to determine the distance to Cepheids by simply measuring their pulsation period. Cepheids were established as the standard candles to determine astronomical distances. So she gifted astronomers a promising method that could measure distances up to 20 million light-years. Now, you might wonder, how does this help us understand our position in the Milky Way? To answer this, we need to introduce another key player, Edwin Hubble. Before the 1920s, many scientists held the view that our Milky Way galaxy was the only one in the universe. Indeed, we had captured images of what we now know as neighboring galaxies, like Andromeda, but they were thought to be star systems within the Milky Way. Consequently, the majority of astronomers believed that the Milky Way was the entire universe. However, as telescopes became more advanced, some started to question this theory. They noticed an increasing number of vague patches in the sky that didn't resemble typical star formation regions in our galaxy. A significant challenge at this time was that there wasn't a precise method to measure the distances to stars. Stars vary greatly in size and brightness. One approach to guessing their distance was based on their apparent brightness. However, a large, luminous star situated far away could seem as close as a smaller, dimmer star. This is where the work of Henrietta Swan Leavitt becomes critical. Leavitt had demonstrated that we could use Cepheid variables to determine distances to galaxies up to 20 million light-years away. Inspired by this, Edwin Hubble decided to measure the distance to the Andromeda galaxy by studying a Cepheid variable star within it. His findings shocked the scientific community. He discovered that Andromeda was approximately 930,000 light-years away, extending far beyond the confines of the Milky Way. Although this distance is about a third of the currently accepted value, Hubble's estimation was enough to confirm Andromeda's location outside the Milky Way, reshaping our understanding of the universe. The discovery that Andromeda is a flattened disk of stars, similar to the Milky Way, sparked a question among astronomers. Where are we located within our own galaxy? Here, the work of American astronomer Harlow Shapley becomes relevant. Initially, Shapley held the belief that everything visible to us was part of the Milky Way, a notion that Edwin Hubble's research disproved. Recognizing his error in the early 1920s, Shapley amended his viewpoint and embarked on a diligent effort to catalog galaxies, documenting as many as 1,249 in just 6 years. However, it was Shapley's work from 1914 to 1918 that played a vital role in our quest to determine our position in the Milky Way. Armed with a powerful Mount Wilson Observatory's 60-inch telescope, the most advanced instrument of his era, Shapley focused his research on globular clusters. These are densely packed groups of hundreds of thousands or even millions of stars that gravitationally bind together to form a spherical shape. They are found above or below the plane of the galaxy. Globular clusters are some of the universe's oldest objects, many dating back over 10 billion years. Shapley discovered that these globular clusters were arranged in a spherical pattern around the galactic core, notably in the direction of the Sagittarius constellation. This was a significant observation. If we were located near the Milky Way's core, we would see globular clusters scattered across the entire sky. However, most of them are only visible near the galactic center, in the direction of the Sagittarius and Scorpius constellations. This indicates that we are not near the center of the galaxy, as William Herschel had hypothesized, but rather positioned towards the outer arm. However, his calculations slightly overshot our actual distance from the galactic center. He estimated that we were situated somewhere between 33,000 and 90,000 light-years away. With the advancements in modern astronomy, we've since refined this figure, finding that our solar system resides near a small partial arm called the Orion Arm, or Orion Spur, located between the Sagittarius and Perseus arms approximately 26,000 light-years from the heart of the Milky Way. The Milky Way is our home, an elegant spiral of starlight spinning in the cosmic abyss. Yet our understanding of its grand design, its vast composition, and indeed our place within it, has often been clouded by the immensity of the task. Until now. Enter Gaia, the European Space Agency's celestial cartographer, silently sailing across the cosmic sea and transforming our understanding of the Milky Way. Launched in late 2013, Gaia embarked on an ambitious journey to craft the most comprehensive and detailed 3D map of our galaxy ever conceived. Armed with a mission to survey approximately 1 billion stars, about 1% of the stars in our galaxy, Gaia has been tirelessly charting the cosmos. Gaia allows astronomers to study the Milky Way as a whole, tracing its structure, dynamics, and evolution. It helps in revealing the galaxy's overall structure, including the distribution of stars, the arrangement of the spiral arms, and the nature of the galactic bulge and halo. This perspective helps refine our understanding of our position within the Milky Way and how our galaxy fits into the broader context of the local universe. Ultimately, the Gaia mission represents a significant leap forward in the field of astrometry, the study of the positions and motions of celestial bodies. It's not as famous as the Hubble Space Telescope or the James Webb Space Telescope, but it's an astronomical game-changer, silently revolutionizing our understanding of the Milky Way. The precise and comprehensive data collected by Gaia is a rich resource that will continue to fuel astronomical discoveries for decades to come, propelling our cosmic journey further into the mysteries of the universe. Recently, astronomers found that a black hole suddenly flipped its direction and is now pointing at us. If you missed this episode, be sure to catch up on this exciting discovery.